Welcome to the Mr. Pier Show, starring Mr. Pier, co-starring Mr. Buchanan as the Enforcer. Welcome, folks. I am going to attempt to do this in one take and not have to stop and restart and stop and restart. So let's just dive right into it. Mr. Buchanan, if you have not yet taken attendance, go ahead and pause the video for a moment while you take care of putting down the attendance on the sheet that I hopefully remember to give you. Okay, thank you. Now that we've taken the attendance, let's, as I've done a few times in the past, I would like to first of all collect the assignment, page 330, classroom exercises, numbers 1 through 11. So let's pass those forward, please. I suppose as you do so, we should once again pause the, Mr. Buchanan, can you hit the pause button again, please? Thank you. I will assume that by this time the papers have been collected. Thank you. Now let's run through these real quickly here and make sure everybody's clear on these definitions. The first section of this chapter was just basically a bunch of definitions. Make sure that you're okay with all of this. Phones in the back row, put them away now. Thank you. By the way, I apologize for the darkness of my appearance. If I put light on my face, then you can't see the screen anymore, so it's just going to have to be dark. My apologies. So number 1, we are to name 3 radii of circle O. What makes a radius a radius? Yes, I will take answers. Yes, I heard that. Okay, yes, exactly. A radius goes from the center of the circle, in this case O, to any point where? Yes, on the circle. Therefore, possible answers. You could say a radius would be segment OT, and by the way, if you're going to name a segment, you need to have the bar on top. Oh, Mr. Pier, I forgot to put the bar on top. Okay, if you didn't put the bar on top, I will forgive you this time, but on the test, you could lose. In fact, on the test, you will lose credit if you don't remember to put the bar on top of a segment name. Yes, a radius is a segment. All right, so we have segment OT. Other radii would be segment OL. We have segment OR. Mr. Pier, what about KL? KL? Are you serious? No. KL is not a radius because K is not at the center of the circle. Oh, I'm so sorry about that. That's all right, I will forgive you. Okay, a radius has to go from the center of the circle to any point on the circle. Does anybody see a particular radius in this diagram that's not immediately obvious? There is one that's not obvious. Yes, you got it. OS. Does segment OS exist? Yes! I'm out of the picture. Segment OS does exist. It just doesn't happen to have any photons of light emitting from it. It's not highlighted here in the diagram, but it does exist. So yes, OS is also a radius of the circle. Alright, that's all there is to radii. So in your 3 answers, all you would have to do is have any 3 segments named that include O and a point on the circle. Oh, by the way, I started all these names with O. Do you have to start with O? Of course not. You can start with LO, you can call it SO, you can call it RO. They're all the same thing. Or TO. All right, moving on. Number 2, name a diameter. There is only one diameter in this diagram that you can name, and that would be segment RL, because what does a diameter do? A diameter has to go through the center, and it has to go from a point on the circle to another point on the circle, through the center. By the way, a diameter is a special kind of what? Chord! Yes, the imaginary student got it. A diameter is a special kind of chord, because a chord is any segment that goes from a point on the circle to another point on the circle. And a diameter is just a special kind of chord. It's a chord that happens to go through the center. All right, let's see. Number 3. Consider segments RS and line. Oh, yes. Here's where the symbols become important. Let's get rid of this. They want us to consider these two things. That and this. Is there a difference? Yes, there is a difference. This is a segment. It has 2 endpoints. This is a line. It has no endpoints because a line has no end. So, what was the question now? Consider segment RS and line RS. Which one is a chord and which one is a secant? There's no mystery here. It's just a question of definitions. Do you know the definition of chord? Do you know the definition of secant? A chord is a segment. RS, that's highlighted here. RS, where's RS? RS is a chord. While line RS, segment, I didn't say that properly. Segment RS is a chord. While line RS is a secant. That's the only difference between a chord and a secant. A chord has 2 endpoints on the circle. A secant shoots through the circle and goes on forever. By the way, to be a secant must touch the circle how many times? Yes, I heard that whisper over there. 2 times. It must touch the circle twice to be a secant. So, number 4. Why is segment TK not a chord? Segment TK, let's clean this up here. Segment TK is here. Why is TK not a chord? Well, that hopefully hits you as being obvious, because point K is right, not on the circle. K would have to be on the circle for this to be a chord. If K were down here, then we would have a chord, but it's not. Next, number 5. Name a tangent to circle. Oh, what makes a tangent a tangent? A tangent touches the circle in only one point. There's only one tangent shown in this diagram, and it would be this tangent. How do you name that? Well, remember from yesterday. A tangent can be a line, but a tangent can also be a segment, or a tangent can even be a ray. What is a tangent? It touches the circle in only one point. So line LH, is a tangent line because it touches the circle only at point L. But what about segment LH? Segment LH is a tangent. It's a tangent segment because it's part of a tangent line. It has to be part of a tangent line to be a tangent segment. Likewise, we can also name a ray LH. Ray LH is a tangent ray because, again, it's part of a tangent line, line LH. All right, we went through all that yesterday, so that should not be news to you. Number 6. There's a special name for point L. Point L is called the imaginary student. Do you know? Yes, I know. Okay, what is point L called? It's called the point at the bottom of the circle. Step out in the hallway, and I'll let you come back in later. You're just being ridiculous. Go. Yes, shoot, shoot. No. L has a couple possible names. We can call it the point of tangency, or we can simply call it the tangent point. As you know, I'm in favor of trying to conserve syllables. So I don't like point of tangency. Point of tangency. 5 syllables. No, no, no. I prefer to call it the tangent point. That's only 3 syllables. That works for me. The tangent point, or the point of tangency. Let's see. Oh, I forgot to check what time I started because I cannot go overtime. Well, this is going to be kind of short anyway, I think. Maybe. We'll see. Number 7. Name a tangent. Oh, sphere. Sphere Q. New diagram. Ding! There it is. I hope that the way I drew this sphere, it is a little bit more obvious to you that it's a big round ball, okay? I drew the plane cutting through it to help you visualize that it's 3-dimensional. Alright, spheres also have chords and secants and tangents and radii and diameters, just like circles do. So for number 7, name a tangent to the sphere. The tangent would be line EF. Or yes, you could have said segment EF, or even ray EF, or ray FE, but this is a tangent to the sphere. Number 8, name a secant of the sphere, and a chord. The secant would be line AB. The secant has to have the line symbol on top. Secant AB. Chord, a chord of the sphere would be segment AB. Segment AB is the chord, line AB is the secant. Next, number 9, name 4 radii. Well, just like with circles. Any 4 segments that have Q as one of the points and a point on the circle as the other one. So you could say QA, or QB, or QC, or QF. There's only one thing here you could not say. Well, actually that's not true. But you cannot say QE, because E is not on the sphere. That's that. All right, moving on. Number 10. We don't need the diagrams for this one. For number 10, if you've got a circle with a radius of 8, this should be pretty straightforward, right? We want to know what's its diameter. If the radius is 8, the diameter is going to be 16. Because a radius is always half of a diameter. So the diameter is 16. Second part of that one. What if the radius is 5.2? Diameter is, yes, 10.4. Oh, what about this next one? 4 square root of 3. How do you double 4 square root of 3? We've been through this before. How does one double 4 square root of 3? You've got 4 of these guys. If you double it, you're going to get 8 of those guys. Diameter would therefore be 8 square root of 3. We've seen that before in another context. And then J. Oh, J? J? What do you do with that? Oh, there's another imaginary student speaking up there. Oh, speaking of the imaginary student, come back in. Yeah, you're forgiven. Come on in. Come on in. Leave Nate alone. Just come in, have your seat. Thank you. All right. If the radius is J, then what's the diameter? Well, this side would have to be J. Yes. Well, therefore, put them together and you would get J squared. No, it's not J squared. That's J times J. We want J plus J. What's a better way to say J plus J? Oh, that would be 2J. Yes, 2J. You've got it. 2J. Number 11. What if the diameter? What if the diameter is given to us as being 14? Then what's the radius? Clearly it is. And the people said, yes, 7. What if the diameter is 13? Oh, I don't know how to take half of 13. Sure you do. 2 ways to take half of 13. Just take half, it's 6.5. Or just put a 200. There, you took half of 13. 13 halves. 6.5. 5.6. What in the world is half of 5.6? Yeah, I know. Take out the calculator. Yeah, lazy bums. Half of 5.6 is 2.8. And then what's half of 6n? Yes, 3n. And we're done with page 330. And now we move on to the new stuff for the day. Which means I can eliminate all of this, right? Yes, I can close this file now. All right. And I just hope that nothing goes wrong with this thing. Everything's looking fine. All right. Now, Theorem 9.1. Got a circle. We've got, what's this called? If that's, assuming that's the center of the circle, this thing is called a, yes, it's called a radius. So we got the radius. Theorem 9.1 says this. If I have a tangent line that's tangent to the circle at the end point of the radius, if the radius and the tangent meet on the circle right there. Theorem 9.1 guarantees that this angle, and we care to guess what this angle has to be, and there's only one reasonable guess. This angle has to be a right angle. It's got to be 90 degrees. Let's go ahead and take a moment to prove that. We're going to prove it indirectly. Remember indirect proof from back in, whatever chapter that was, maybe chapter 6 or something, I don't remember. We did indirect proof. To do an indirect proof, you start by assuming what? That the thing you're trying to prove is actually false. That's right. You start by trying to prove that I'm sorry, reverse the tape here. You start by assuming the thing you're trying to prove is actually false. We're trying to prove that if this is a tangent and this is a radius, we're trying to prove that that's a right angle. Let's temporarily assume it's not a right angle. But wait a moment. Assuming that's not a right angle for a second, let's redraw it so it's not a right angle. Okay. There has to be a line from this point to this line that is at a right angle. That's an old theorem from some old chapter, that from any point to a line there will be one perpendicular. So if it's not here, it must be someplace else. Let's draw it over here. But that looks ridiculous. Yeah, I know. When you do a diagram for an indirect proof, it always does look ridiculous because you're saying, suppose that the true theorem is not true. And it produces a weird diagram. True. Now, if this is the right angle, we know again from a previous chapter that the longest segment has to be the hypotenuse. So now, if this is the right angle, where's the hypotenuse? It is here. But wait a moment. If that's the longest segment, what's going on here? Because this is longer than the radius. This goes beyond a radius. This guy is longer than a radius. How can the longest side, the hypotenuse, be shorter than this side? It can't be. It doesn't make any sense. Contradiction. That means that the thing that we were supposing is actually false. I'm getting a headache. Yes, I know. We started by supposing that this was not a right angle. We just showed that that leads to a ridiculous contradiction. Therefore, guess what? This must be a right angle. That's how indirect proofs work. Will I ever ask you to do an indirect proof on any test or even homework assignment? No. Relax. Breathe deeply. It's going to be okay. All right. What? There's another phone. Get rid of the phone now. And no eating in my classroom. ditch it now. Thank you. All right, moving on. So theorem 9.1, if this is a radius and this is a tangent, then this will be a right angle. There's a corollary to that. I call this one the ice cream cone corollary. The ice cream cone corollary says this. If I've got a circle, and if I have two tangents, let's change colors here. If I have two tangents to the circle that happen to meet out here at some point. Two tangents to a circle meeting at a point out here at their endpoints. Thus, the ice cream cone corollary. Because it looks like an ice cream cone, I think. Don't you think? Okay, sorry. Ice cream cone corollary. The corollary of theorem 9.1 says that these two segments will be, oh, excuse me. One moment, I need some tea. Thank you. Ice cream cone corollary, the corollary of theorem 9.1 says that these two segments are guaranteed to be congruent. Guaranteed to be congruent. That's going to come in very handy in some later theorems and in some homework problems and test questions. We now move on. Checking the clock. I think we're okay. I'm hoping to leave you with some time to work on the assignment. We shall see here. Moving on now to the bottom of 333. Oh, cool page number, 333. Bottom of page 333, looking at theorem 9.2. Theorem 9.2 is the converse of theorem 9.1. What's that mean? 9.1 said, if this is a radius and that's a tangent, then this will be a right angle. Theorem 9.2 says, if this is a right angle, then this has to be a tangent line. Theorem 9.2, if a line in the plane of a circle is perpendicular to a radius at its outer endpoint, then the line is tangent to the circle. So theorem 9.1 says, if this is a tangent, then this will be a right angle. 9.2 says, if this is a right angle, then this will be a tangent. They are whats of each other? A little louder? Yes, yes. They are converses of each other. Remember what a converse is. If P, then Q. Converse? If Q, then P. All right, moving on. I'm over on page 334 now. On 334, we have some new definitions. Clear the screen. Okay. First, consider this. A circle. And I'm going to draw a triangle to the best of my ability here. Oh, that's pitiful, but it'll do. That's not so bad. All right. I've drawn a triangle around the circle so that the circle is tangent to all three sides of the triangle. 3 points of tangency there. Having done that, there are two ways we can describe this situation. By the way, what does CIRC, circ? It's the first 4 letters of the word circle. It basically refers to things going around in circles. What does it mean to circumnavigate the globe? To circumnavigate the globe, and I'm terrible at history, but it was Magellan, right? Magellan, who was the first to circumnavigate the globe, go all the way around the earth. Please, if I'm wrong on that, correct me, because I don't want you going home tonight thinking that the wrong person was the first one to circumnavigate the globe. But to circumnavigate is to go around in a circle. What other circums do we have? Circumstance. How would that apply to a circle? circumstance. The situation around you is your circumstance, your stance, where you're standing. Circumstance. I'm standing in my situation that circles me. It works for me. Anyway, we will say that this circle is, or let's start the other way. The triangle is circumscribed around the circle. The triangle is can I spell this? Yes. Circumscribed around the circle. Circum, referring to going around in a circle. What did the word describe refer to? What was a scribe back in Bible days, in New Testament days, probably even now? What's a scribe do? A scribe is known for copying the Bible, for writing something. To scribe is to write. So circumscribe means to write it around the circle. We have circumscribed the triangle around the circle. Now on the other hand, the other way to look at this, we can talk about the circle being inscribed in the triangle. So the circle is inscribed, which makes sense because the circle is written inside the triangle. So we can say the circle is inscribed in the triangle, or we can say the triangle is circumscribed around the circle. Okay. You do have to be careful how you pronounce circumscribed because it can come out sounding kind of funny if you're not careful. Now, we're just about done here. Consider this now. Two circles. Suppose I have a tangent line, this tangent to both circles at the same time, such as this one. What do you call it when, say, two people share the same something or other? If you have a friend who has, I'm out of the screen, I'm sorry. If you have a friend who has exactly the same phone as you, you might say that the two of you have something in, common. These two circles have something in common. They share a tangent line. Therefore, this is called a common tangent. They have a common tangent line. Do these two circles have any more common tangents? Yes, there's another common tangent. There's the one that goes right across the top. Yes, imaginary student, right across the top. There's a common tangent right up here. Are there any other common tangents? No! Oh, yes, there are. Think about it. What's a common tangent? It's simply any line that's tangent to both circles at the same time. Yes, I see that hand. Yes, you're exactly right. There's one that goes through like this. Are there any others? Yes, there's one more just like that one that goes like this. So with these two circles, we have 4 common tangents. Now, here's another definition. I don't know why, but this definition seems to confuse students. Well, I think I know why. There are a couple points here the book does not make very clear. But because these two tangents pass between the circles, they are called common internal tangents. They're inside here. They are internal tangents, which makes it pretty easy to guess what the other two are called. External tangents. Yes, common external tangents. So with two circles like this, we have a pair. We have 2 common internal tangents, and we will have 2 common external tangents, and that's all we're going to have. That's the end of it. Now, consider this. What if the circles look like this? How many common external tangents would you have? There's one external tangent. There's another external tangent. So we have two common external tangents. How many common internal tangents? None? I don't know. Well, what's a common internal tangent look like? It has to go between the circles, and it has to be tangent to both of them. There would be one. Yes. Where? Right down the middle. Yes, one right down the middle. These two circles have one common internal tangent and only one common internal tangent. I see. Good. Hey, how about this? Clear the screen. What do the circles look like this? How many common externals? Yep, I heard that. Two. One and two, just like the others. How many common internals? How about this one? Well, is that line tangent to either of those circles? No. Nope. How many common internal tangents? None. Exactly right. No common internal tangents. Let's see, what else can we do? Let's jump to the last definition of this section, and then we're done. Last definition. These two circles are said to be tangent to each other. Yes, circles can be tangent to circles. Makes sense? Because, well, I didn't draw it super well here, but with a little bit of imagination, these two circles touch each other in just one point, so we say the circles are tangent to each other. But wait just a moment. One moment. Are not these two... Oh, that was terrible. I can do better than that. Try that again. Okay, that's a little better. Are not those two circles also touching in only one point? Therefore, these two circles are also tangent to each other. So there are two different ways you can have circles tangent to each other. You can have that, or you can have that. Now we have, to describe those, we have some special terminology. Because this circle is inside the other one, they're tangent on the inside of the big one. We call these guys internally tangent. Internally tangent circles.